Hello and welcome back, everyone, to part 2 of the Broyden method. Hopefully, I'm a little more collected. That's already been tested. It's very late, no promises. That should mean we've got a lot of fun, humorous quips, but I can't promise anything. So, in this one, we're going to be showing how a very simple Broyden method might work for a nice, simple equation like this terrifying beast, the one we've all been dreading. I think we can do it. So I've gone ahead and I've done some pre-work here to make it all a little bit easier, so we're not writing down a whole bunch of really bland, boring equations that are more so functional than anything. We've imported Jax and Jax NumPy. It's a NumPy package, Jax, a few other fun features we'll need to be using, including some variable stuff. Configuring, including Jax enable x64, that means we can use a lot more power, which is excellent. I pulled in some things in SciPy.optimize. You might remember minimize, press root. Non-linear constraint will be important for later on. We've got some inequality systems because you've maybe got the wrong number of variables lying around, or some inequality you're constrained to. You remember the constraint we had last time. That seems a bit unequal at times. So, that's all later. And we defined a simple basic function 1. Simple and basic are in quotes. It's an absolute terrifying beast of a function. A quote-unquote simple basic function 2. And we'll get back to that one. We've got a Rosenbrock function. That's the one we want to fix. We've got our equality constraint and equality gradients. A gradient is just that Jacobian we saw earlier. Back here at the top, where it's, del f1 over del x1, yada yada, del fn over del xn, and then that mess there. And then we've got the same thing with inequalities, where maybe it's not all very pretty. We might have some things going, inequality bound to some function. It's not very nice at all. We don't like it, but we'll have that set up ahead of time, so it's less work. You don't have to watch me type out some really disgusting function. So, with that, let's get to broadening. We'll set up a nice X matrix here. At Jax NumPy, we can just do some zeros, and we'll say, make it 2. Give me 2 zeros. I'll also like a Jacobian, please. And I'd like that to be Jax dot Jacobian of, what is our function? Well, I'd say our function is function 1. Oh, and I'd like that to be using x. And we'll say that f, for ease of not having to write function, is just going to be function 1 evaluated through x. So, with that, let's start Jacobian. Now, it is iterative, like Newton. Unfortunately, we have to address his method. Something about apples and calculus, maybe light. I think he was famous for that. I don't know, nerd stuff. We'll say for I, that's not an I, in a nice range. We'll do 20 iterations for now. And we'll say that x plus, so our bit further x, is going to be Jax NumPy. Give me that nice linear algebra. Linear algebra, thank you. I'd like you to solve, let's do the work all for me, j negative f plus x. You remember that from back here somewhere. We've got our x plus, I'm sure it's here somewhere. Close to there. It's kind of fallen in this mess. Actually, yeah, it's that one. So, should be. And we'll say x plus, and then we'll say our change in x is going to be equal to x plus minus x. And we'll also, to save up space, we'll go ahead and say that our function plus is then going to Yeah, I can do that. Is going to be function 1 evaluated x plus, so our bit further x. Then we'll set f x equal to function plus and x plus. And then, just so we know it's actually doing things, we'll have it print x and there should be f, but we'll say f plus for good measure. And then if things start really like not changing, meaning we're pretty close to some solution, it's narrowed on some local minima, slopes about 0, we'll go ahead and say you can do a nice bit of jp dot linear algebra dot normalize that fp is less than our machine precision value, which is epsilon at 1e minus 12. It's basically 0. Go ahead and stop doing math. You're done. And we'll go ahead and say that j... Oh, that's inside. J... As you might remember, j is then going to be the modifier j. It's j plus a bit of outer multiplication here. It's an outer product. I'd like function plus delta x. And then that should all then over be Jack's numpy dot linear algebra dot norm dx squared. That helps us kind of narrow it in a bit. That is no, not that one. It's that one in a less pretty function. It's that version there. It's a whole j plus thing. And with that then should do it. So if we run this, I should kind of Newton-Broyden something it. And it's going to complain, I don't have a GPU to fall back on because this is Google Colab. It's just basically a dummy computer. There's no graphics card. It's going to do its best on the CPU, but otherwise it can GPU calculate, and that's much faster. So based upon this, it seems potentially like our function might be. That's going to bother me immensely. Hold on. Let me change to print. F quote split new line and export those. That should do it. Yes. Oh, that's why. I'm very stupid. It actually was doing that. Oops. I forgot that it's 2 for each. My bad, everyone. I don't know how math works. I forgot x and fp should both be 2 values. So our x here is going to be 1, 0. Our fp is going to be that and that. And then, you know, it's going to keep iterating. It's going to say, no, that's different, right? Maybe it's here, maybe it's there, maybe it's there. Eventually it decides, the solution is at an x1 of 0.9313663 and x2 of 0.197563991. That's basically our solution. That's pretty good. It's noticed we've got a minima or a maxima. We've got a minima here. The slope ain't changing a whole bunch. We're probably at a nice point on the function. Cool. But we can do better. Let's make this a nice packaged function. Let's define our Broyden, if you will. I'd like a function input, please. I'd like an x input, please. Jacobian if we want to import one ourselves, but for now, we'll just set it to none. That's, for those of you who say a C language, that's your null. That's nothing. There's nothing there. We'll set a max iterations at 100, and because I like actually having that make sense, we'll have a verbosity scale. As my professor defined it, it was verbose. I prefer verbosity. It's a bit longer, but it makes more sense for what we're doing here. We've got a J. You might remember that J. It's going to be Jax dot the Jacobian of input function, and then to X if J is none. It doesn't have an input J, perhaps. Otherwise, if it does have an input J, go ahead and just do the J you were asked for. I've shown this a few times before. That's a nice shorthand way of writing, an if gate. We've only got 2 outcomes, and you don't have to dedicate 4 lines to what should be 1. Let's do a J inverse. And let's do J and P dot linear algebra. Please invert J. You might remember we need some inverted J's, and F is defined as a function X. So we're going to nicely just kind of pull this part. That should work. I'm lazy. I don't like writing more than I have to. Fun way of doing this. Tab. Collect it all. Select it all. Press tab. Now it's all inputted. But of course, we have to do some math because we can't just jnp.linearalgebra.solve it to ourselves. So x plus is going to be x minus J inverted at F. What does an at mean? That's scary. Are we emailing the F? Is F our domain? Is J inverse my hip new email address? No. That is your matrix multiply. And then from there, we can pull up our... Oh no. Did I set dx? I did. I compressed it down. That's why. But that should then be just a function, please, at xp. So dx and fp should then be equal to x minus x, and the function fp, f should be set to fp, x should be set to xp. Actually, I'm going to say a little bit nicer, and I'm going to say that fp is equal to the function xp. I'm going to decondense that because it's a little bit nicer to look at that way. So we've got our 2 pluses, we've got our change in x, and then we've got the 2 reassignments combined. Now, we're going to make it a bit more, perhaps, in case I don't want to have to constantly see all that garbage spat out, we'll say, because I might not want to see that every time, I might want it to just do its job. So we'll say an if verbosity is at least none. Well, it's over none. It can't be none. At least 1. I like that form better. And we could do a true-false here, but we're going to make the function a bit more bulky and verbose later on, so we want varying levels of verbosity. Please print me x and f. I might want to see that. So yes, I was right. We can just do f instead of f plus. And then, of course, if the j and p dot linear algebra dot norm, if that ends up being basically none, go ahead and break it. Now, in order to make our life a bit easier, you might remember that Sherman-Morrison we did. That's important for calculating our new j, because that j method there is a bit slow and a bit maybe not do anything at all. I do it on that line, don't I? I do. So we'll set our u. So as you might remember from that Sherman-Morrison, j and p dot expand dimensions, please. Which you can leave it just there. I'd like fp expanded on dimension 1, please. And then I'd like v to be set as j and p dot expand dimensions of dx, again, 1, please. And then remember, there was a divided. We need that j and p dot algebra dot. Okay. I'm going to do something between clips here, between episodes. I'm going to set linear algebra to be imported as its own packet because this is slow. I like typing out linear algebra this many times. That's a thing you can do. I'll show it once it's done later on, but for now, we'll just truck on through. This is all we need to tackle at the moment. And then squared, as you might remember. And then our new j inverse is going to be our old j inverse minus our boy old j inverse. Matrix multiply u, matrix multiply v. You can do that. These fun arrays. Matrix multiply the j inverse again, and divide it all by 1 plus v transpose at j inverse at u. And that is the Sherman-Morrison for Broyden method. Smile. Just a regular smiley face, please. He's very happy about this. That's the computer. The computer's happy because that's easy math to do. And then, of course, I might want these things return x and f. They seem helpful. Alright, then, let's do... Actually, I can improve this. Potentially. I'd like that to be that. And you'll see why. Because what we're going to do is x is going to be equal to j and p dot zeros like same shape and type. I'd like it to be the same shape as... Oh, no, wait. Take that back. I can't do that. I got a little overzealous. I actually cannot spit out such an equation. I hoped for a moment there I might be able to shorten it, but alas, I can't. I'll go different. It's SDX. That's okay. You're seeing in progress learning. Now I'd like to Broyden this, if you don't mind. And I'd like it with function 1 and 2 zeros, please. See what this does, or if it screams at me like I'm a madman. Alright, that's very good. So that got us... And you might remember that 9313663. I'm not reading it again. Yes, that got the same things, but it doesn't spit all that out. Is it still there? Were you not? If I set verbosity to 2500. I'm a mad lad. I'm unstoppable. Yes, that's at least one. So it's verbose. We can chop that out and make this a bit smaller. There you go. There's Broyden implied. Not this silly, not quite Broyden. A true blue Broyden. Rosenbrock, you've met your match. What's that? Slack variables, Lagrange multipliers, inequalities? Oh no, ladies and gentlemen, it seems we've got a lot set out for us. We'll get to that next time.